Hey everybody, welcome back to chemistry. If I can blow up the slide. It says as follows. Bromination of isobutane is a two-step reaction. And so if you look to the right of that slide, you can see there to the right of the word step 1, there is a chemical reaction. And then to the right of step 2, there's another chemical reaction. And then below that, you're basically adding those two reactions together to get something called the overall reaction. If you look at that lower table there, what you are given there is the amount of energy needed to break each of those different kinds of bonds in kilojoules per mole. So for example, if you have a bond between two hydrogen atoms, it'll require 436 kilojoules per mole to break, and that can be expressed as a change of enthalpy in order to take those two atoms that are bonded together and break them into individual atoms. Okay, if I can lower the slide. Okay, so what I want to do is I really just want to focus on step 1 of this reaction and figuring out what the change of enthalpy is for this reaction, and then I'll let you do the rest. Okay, so first we have to sort of look at the structures and interpret them. This can be a little bit difficult to see. So here we have a molecule and there's a central carbon, and then leaving the carbon you have attached to it CH3. Same thing here to the left and same thing here to the bottom, but then to the right we have just a single hydrogen atom. So what I want to do is I want to redraw this so it makes a little bit more sense. So I'm going to show you how it may be redrawn. So you have carbon here, and then going up it's bonded to a carbon, and then it says H3. It looks like this. And then here, carbon going to the right, it looks like this. And then let me do the rest, and then I'll get back with you. Okay, so what I've done is completely written out all of the bonds for each of these structures. And so here, this is what the first molecule looks like. Now here we have bromine with a single dot, and so one of the things you know is that bromine has 7 valence electrons, and so they give you bromine with a single dot, which is pretty confusing in my opinion. What they should have done is they should have drawn out the 7 dots like this, and then this one here should be a dot as well. So just know this is the same thing as bromine with a single dot. And so chemists just get lazy a lot of times and leave out lone pairs. But you should just be aware that this is bromine with its 7 valence electrons. And here bromine is an atom. It has 7 valence electrons. And what you'll notice that it happens to be an atom with 1 unpaired electron. And so that atom here is going to be called a free radical. Okay, here on the right, this molecule here is the same as the molecule on the left, except we're removing a hydrogen and we're leaving 1 electron here on this carbon. Now, a couple of things about this. So first off, this is not a mistake. You might think that there might be, say, 2 electrons here, like with a lone pair. That might be possible in some reactions, but here, this is not a mistake. It's just 1 electron. So here, this molecule is also a radical. And so you might remember what a radical is. A radical is a molecule that has single electrons. Now, one of the things I've been saying to you is that whenever you have carbon, nitrogen, oxygen, fluorine, or neon, you must have an octet of electrons. You can't have any more than 8 or any less than 8. This is an unusual case where you can have 1 less than 8. So this carbon actually has 7 electrons here. And so again, it's a radical. Here, this molecule here is normal. So let me go ahead and add in the lone pairs here. And so that's fine. Okay. So you may be wondering what is going on here, how this reaction is going. Let's go back to this molecule here. You see this bond here between carbon and hydrogen here? Let me erase it here. And then what you have here is 2 electrons here. And so what happens in this reaction is here we're going to break this carbon-hydrogen bond. In other words, we're going to break the 2 electrons here, and we're going to leave 1 electron on this molecule, and the hydrogen with this electron is going to bind to bromine. And then we're going to form a bond here between hydrogen and bromine. So that's the basic idea of the reaction. So what I'm going to do is I'm going to clean up the board a bit, and then I'm actually going to solve the problem. Okay, so what they want you to do is figure out the enthalpy change of this reaction here. And so there are a couple of ways you can do it. So one way you can do it is by using this formula, that the change, the enthalpy of the reaction is equal to the sum of all bonds in reactants broken minus the sum of all bonds in products formed. So let me explain what you would have to do here to solve it in this way. So here we have a reactant here, and you can see that this reactant has a lot of bonds. And so, for example, there's a carbon-hydrogen bond, and then there are several carbon-carbon bonds, and then also implied is that there are several carbon-hydrogen bonds. And so what you can do is you can work out how much energy is required to break all these bonds. And then here you would have to figure out, well, in this molecule, here we have the same thing, but now all these bonds are being formed here, and you can add them up. But there's really an easier way to solve the problem. I think what thing you can sort of notice here is that between the left side and the right side of the reaction, really there isn't too much difference in the bonds. And so, for example, here on the left side, we have a carbon here bond to the left to another carbon. This is retained in the products. And so you can see most of the bonds here in the reactants are retained in the products except for two bonds. And so one bond here is this bond, this carbon-hydrogen bond. This is being broken. And then here on the product side, the bond between hydrogen and bromine is being formed. And so really all you have to do is subtract the energy of the broken bond from the energy of the formed bond. So this, we're not going to use this here. That's too much of a pain. Instead, what we're going to do is we're just going to have the bond energy of reactant bond that is broken minus the sum of the bond energy of product bonds that are formed. Here in this formula it says bond energy of reactant. I should say bonds with an S here. So you would have to sum up all of the energies of the bonds being broken. But here there's only one bond being broken here, right? And so you can look up its energy. And so if you look carefully at that table there, I think you want to go to the next to last one. That is the one that's being broken. And so it's going to be 400 kilojoules per mole. And then we subtract from it the sum of all the bonds that are being formed in the products. And we only have one bond that's being formed. So we subtract from it that energy, which is going to be 366. So when you do that, I get an answer of 34 kilojoules per mole. So what I did here for step 1, you should do for step 2. And then what you can do in the overall equation is you can solve it by noticing in the overall equation on the reactant side all the bonds that are being broken and subtract from them on the product side all the bonds that are being formed. Okay, thank you for listening. We'll see you next time.